Okay, so sorry about that. As I was saying, I am MPI. I will be hosting the Topic 10 revision session as well as others. Topic 3, I think, Topic 12 as well. But I'm still working on this. I'll keep you posted when I do finish the presentations. But anyway, Topic 7. I think it's called atomic and nuclear physics. It's mainly particle physics, so that's what I'm going to be calling it. But I don't exactly remember what it was, the name. But anyway, so we'll start with some definitions, which you can be asked in the exam. Give me 1 second. By the way, I'll be right back. Energy levels. This is topic 7.1. I'm gonna here set some definitions. I will post this later so that you guys can check it out. But these are definitions that can be asked in exams. They have been asked in exams in the past. So I just put them out here for you to kind of memorize. Anyway, so an emission spectrum is a set of wavelengths that can be emitted by a gas, which are emitted by a gas when you subject to very high temperatures, so that or you expose it to an electric field. It's kind of like a barcode. So it basically identifies any gas. You can identify any gas by its emission spectra. It's used a lot in astrophysics when you want to know the composition of a star. For instance, you use spectroscopy. You analyze the emission spectra or the absorption spectra rather, which I'll get to in a second, of a star, and then you can see what wavelengths it's absorbed, and you can tell, okay, the star is made from iron, it's made from helium, it's made from whatever types of gas. You can also use it to find out what the atmosphere is made of. Absorption spectra is kind of its counterpart, so the set of wavelengths that are absorbed when white light is transmitted to a gas, and they align perfectly with the black parts of the emission spectra. So if you remember the spectrum, or the visible spectrum, the electromagnetic spectrum is like this kind of continuous wavelength from, I don't remember how many, but it's like this continuous spectrum. And if you look at the absorption spectra of a gas, you'll see that there's certain parts that are like blacked out, and those are wavelengths that have been absorbed by a gas, and you can tell what gas it is because each gas absorbs different wavelengths depending on its atomic composition. Then a photon is a particle of light that contains an energy package and linear momentum. Its energy is given by the formula E is equal to hf, where h is Planck constant and f is the frequency. And yeah, we'll get up when I go over quantum. You'll see it's but I'll talk about it in more detail. But photons are the particles of light. We're not talking about wave. We're not talking about wave light or like the wave behavior of light in this one. We are focusing more on the particle-like behavior of light. Those of you, I'm sure most of you have heard of the wave-particle duality. In this case, we're focusing on the particle nature of light, the corpuscular nature, I believe it's called. Energy levels, or the energy in an atom. Well, the energy in an atom is discrete, so it can only have certain values for its energy. It's not like continuum. You can't have any value. It can only say it can only be integers, for example, and these values are what we call energy levels. So you can only have like say HF or 2HF, 3HF. You can only have a certain amount of energy. Atomic electron transition are trips that the particles make. A photon is emitted when an atom transitions from a higher energy to a lower one, and a photon is absorbed when the transition is from a lower energy level to a higher one. Wait, can't you hear me now? Again? Oh, okay, cool. Anyway, this is an exercise. I encourage you to do it. I'll have the solution in a second, but the transitions shown in the following figures, which transition emits a photon with a longer wavelength? I'll give you, like, say, a minute to answer, and if one of you wants to unmute themselves once the minute is over and tell me why they think it is, why they think the answer is what they say it is, feel free to talk about it. I mean, if you can't unmute yourselves, just again, yeah, some of you did say it. So remember that so here's the full worked solution. So you can show, since E is equal to HF and frequency is equal to it's C over lambda. This is something that you can, it's a pretty straightforward proof really. You can show that the energy is inversely proportional to wavelength. So you need to look at the least energetic transition, and that will have the longest associated wavelength. And so that will be the transition from P to 2. Since that's a shorter transition, it will have the lowest frequency, or lowest change in frequency, and therefore the highest wavelength, since it has the least energy. There's the smallest change in energy between the two. On the other hand, the shortest wavelength will be the one from 3 to 1, because for that same reason, there's a higher change in energy, which means the frequency is smaller and the wavelength is bigger. Here's another exercise. Find the wavelength of a photon emitted in a transition of two energy levels at different 1.9 electron volts. I mean, this one is pretty straightforward, but if any of you want to post the answer in chat, feel free to do so. If not, actually do post the answer in chat if you guys can come up with it. Okay, so the first thing you need to realize, the formula you posted is correct, Ash, but you first need to realize it's very important to have your energy in joules when you're doing, unless you're using Planck constant in electron volts, which I guess is another way of doing it. But if you're using Planck constant as 6.63 times 10 to the minus 34, it's really important you first remember to change it to joules, your energy. So first convert electron volts to joules, and then just use the formula you mentioned. So Hc over E is going to be lambda, which you can solve from the previous exercise, and you get that the wavelength is 654 nanometers, which I believe is red in the spectrum, but I'm not sure. Anyway, so second part is forces in the nucleus. So there is 4 fundamental forces, but in the nucleus there's only 3 that are dominant. The force of electrical repulsion between electrons, the strong nuclear force acting between the nucleons, and the weak nuclear force responsible for beta decay, which we'll get to in a second. The strong nuclear force has very short range. So the nucleons are only attracted by the first neighbors. Conversely, the electrical force, which has infinite range, implies there will be repulsion between all protons. And the presence of the strong nuclear force prevents the atom from flying apart, because from electrical repulsion you have like-minded, not charged, so positive protons repelling each other, and the strong nuclear force is what keeps them together. Anyway, so next is radioactivity and nuclear stability. So here are some definitions again. The mass number is the number of nucleons in the number of nucleons, which nucleons is protons and neutrons, and that's the just number of nucleons in the nucleus. The atomic number is the number of protons in the nucleus, and the nucleoid is a nucleus with a specific number of protons and neutrons. These possible set of nucleons are characterized by a mass number A, atomic number C, and a number N equals A minus C neutrons, and they were separated into 3 groups. So isotopes, which have a different number of protons and neutrons, so they are the same element, but isobars, which have a different mass numbers, a different number of nucleons than protons. Isotones, which have the same number of neutrons as they have protons, and isomers, but actually this won't be asked in the exam, that hasn't been asked in any of the past papers I've done, but isomers are, so these are like the same particles, so they are the same element, but they have a different number of things. So like for instance, But this won't really be asked in the exam. So atomic mass unit is it's the fundamental unit we use to measure the mass of an atom. The standard unit in the SI in the International System of units, and it's just defined as 1/12 of the mass of a neutral atom of carbon-12. And then you also have the activity, which is the ratio of disintegration measured in becquerels. So it's 1 becquerel just means that it's 1 disintegration per second. Are there any questions so far, or can I skip ahead? Can I continue? All good? Okay, cool. In this exercise, it's really straightforward. So just determine the number of protons, neutrons, and electrons in the following elements. Should be really straightforward. So I'll give you like 15 seconds to do it. Yeah, so the carbon-12 has 6 protons, since, well, actually I don't know if you can see the pointer. So 6 protons, 6 electrons as well, since it's neutral. And then 6 neutrons, since 12 minus 6 is 6, and it has 12 neutrons, so therefore it must have 6 neutrons. Indeed. And helium, same thing, 2 protons, 2 electrons, 2 neutrons for that same logic. Oops, actually, alright, that's the next slide. But yeah, so these are really straightforward. I think you get a couple of them in the exam, mainly in paper 1, but really straightforward, some simple maths. If I did forget to add, if there's a plus, is it? Maybe I did get them wrong. Hold on. Could be. I'll check later. I'll ping you later, but I'm pretty sure this is where you're right. It could be that I got them wrong. At the moment I actually don't know, but I'll check and I'll update the presentation accordingly if that is the case. Anyway, moving on. Radioactive disintegration. Okay, I apologize for that. Then I made a mistake. When I upload the presentation, I'll change it. I'm sorry. Radioactive disintegration. This is a really important part. So of the 2,300 known nucleoids, less than 300 are stable. And by stable, I mean there's no type of decay, so they just stay like that for a very, very long time, or basically forever. Nucleus, so there's this principle in physics which basically says that every system tends to its state of less energy. And there's a bit more to this. There's a semi-empirical formula, and there's some values and things, but I'm not going to go into that this because I just learned about it this year in physics, and I'm in my 2nd year, so I don't think IB will ask you to be able to say why transitions occur and like a value of stability and stuff. But anyway, what can happen and what does happen is that an unstable nucleus reduces its energy and becomes more stable by emitting particles and energy. So it tends to its state of less energy. There will be a time, like a topic 12. Yes, there will be a topic 12. I will get to that in a sec. I'm still preparing that one since I had to hand in some stuff from uni. But yes, that will happen soon. We call this emitting of particles and reducing of energy radioactive decay. There's 2 characteristics to a radioactive decay that are very important to remember. It's a random process. You don't know, it's impossible to say what nucleus will decay and when it will do so. And it's a spontaneous process. A decay cannot be induced and it cannot be prevented. There are other types of processes that release energy that can be induced, but a radioactive decay cannot. It's completely random and it's completely spontaneous. There are 3 types of radioactive decay. There's alpha, there's beta, and there's gamma. Alpha decay will consist of emissions of alpha nucleus, which are essentially helium atoms. beta emissions of rapid electrons, and gamma is emission of photons. So photons are represented by the Greek letter gamma, and they don't have any charge, so they are usually represented with a 0 and a 0, or maybe just with a gamma. It depends on who you see. But anyway, alpha and gamma emissions are discrete, which means they only have a set, like they can only take certain values, while beta emissions are continuous. They can take any value. These emissions are ionized. We can bombard electrons to create more excited ions. And for a given energy, radiation has the greatest ionization, but least. For a given energy, alpha radiation has the greatest ionization, so it's the most charged, but the least penetration. So, for instance, alpha radiation, I think, cannot even go through a sheet of paper. It definitely cannot penetrate your skin. But gamma radiation, which isn't charged, has the least ionization, but has the greatest penetration. So gamma radiation can, well, actually, it's the kind of radiation that gives you cancer and mutates your cells and stuff. And that's gamma radiation. It has a lot of penetration. It can really just, it can penetrate through, I think, even lead, or not, no, it can penetrate through steel. It can penetrate the lead, but it can easily penetrate your skin, for example. So here are some examples of radiation. This is alpha radiation. So you have like I actually don't remember the name of the element, but it decays to uranium. I think that's plutonium. And as you can see, actually it could be wrong. I'm pretty sure that's supposed to be a 292 instead of 294, because conservation of nuclear isn't conserved here. But so forget about this one. I'll change that later. But for instance, here you have a 238 uranium decays to 234 thorium and an alpha particle, which 234 plus 4 is 238, so you have like nuclear number conserved, and same for the bottom. And here you have polonium decaying into lead, which I still think is wrong. Maybe there's a bunch of alpha particles. I'll check these later. These are definitely wrong. I don't know why they're here. This should probably have 5 particles, or this should be a 230. I'll check. But yeah, so just to remember that when you have alpha decay, yeah, B's definitely correct. The other two are not, from what I'm seeing. I'll check those later. I probably made a mistake when I was typing them in. I apologize for this. But yes, that's definitely not right. You can't have 294 decay to 238. That's impossible. You should decay to 290. But we'll get to conservation loss in a second. Just this one is definitely correct. These ones are the other two are definitely not correct. But I'll change those later and update the presentation and tell you about them when I do so. Examples of beta radiation. In beta minus decay, an electron and an electron antineutrino are formed. I'll get to antiparticles in a second, but it's basically the counterpart of a particle. And neutrinos are just there for conservation loss to be obeyed. It's conservation of momentum that neutrinos there for. Because without neutrino, the momentum isn't conserved, and that's bad, because it makes the reaction impossible. That's actually how neutrinos were discovered, or they were first theorized because conservation of momentum wasn't obeyed. So here, actually, well, don't know if these are right. This one is definitely right. The second one is, and the third one is as well. The first one, I don't think it is. Well, I think, yeah, because it's nitrogen is supposed to be 13, not 19. So it's supposed to be 14.7. But can I speak that out louder? Yeah, sure. Hold on, let me bring my computer closer. Is that better? I usually use a mic, but I don't have a mic with me at the moment, so I'm just using the laptop speaker. So anyway, so that's beta minus decay. It's an electron and an electron antineutrino. And in beta plus decay, a positron, which is the antiparticle of an electron, and an electron neutrino are formed. So you have reactions like these at the bottom, which actually this one is correct, this one isn't. Where the fuck is everything wrong? I don't know. I'll check those later and update them. These are definitely wrong. I don't know how the hell I made so many mistakes when typing them in. I literally copied these from a book. Anyway, examples of gamma radiation. So these are the easiest ones, since you basically end up with the same element you started with, just in a less energetic state. Yeah, I know, right? But I'll update those later, and when I post the presentation, and possibly when I upload it to YouTube, I'll re-record it. But anyway, so gamma radiation is is the easiest of them all. Really, you end up with the same element you started with. This means, or there's another way of saying this, which sounds more fancy, saying there's no transportation. So the element doesn't change. You start with nickel, you end up with nickel, and just simply in a less energetic state. So if we go back to here, these transitions from the same element, these would all be considered emissions of gamma radiation because you're emitting a photon. The law of radioactive decay, even though radioactive decay is random, as we stated earlier, you can't exactly predict when it will happen. You can formulate a law of radioactive decay, and it just simply states that the energy of decay is proportional to the number of nuclei that are present. This is a differential equation, which some of you may know how to solve, but anyway, that's just it's just an inverse law, and that it implies that there is an exponential decrease in activity as time goes by, and the interval in which the activity of a sample is reduced by a factor of a half. So if you start, remember that an activity is in the first example, if we asked to find the wavelength, the shortest wavelength, it would be from 3 to 2. Because it's the shortest transition, and the shortest wavelength. Yeah, my bad. The shortest wavelength would be from 3 to 1. Yes, since that's the most energetic. So you have the highest frequency in there for the shortest wavelength, and the longest one would be from 3 to 2. Yeah, my bad. And then going back to half-life, it's the interval in which the time of the activity of a sample is reduced by a factor of half. Remember that the activity is the amount of disintegrations per second, so when the amount of disintegrations per second reduces to half of its original value, you say that one half time has passed. So here's another exercise that you guys can do. So the half-life of an isotope is 4 days. Find the fraction of the original activity 12 days past. I'll give you a couple minutes, and then I'll show the answer. So I see some of you are posting their correct answer. I would encourage you to, if you know how to spoil things, do spoil them, since that makes it easier for other people to try the exercise. But yes, it is 1/8. So after 12 days, 3 half-lives have passed. So 12 divided by 4. Since each half-life the activity decreases by half, after 12 days the activity will be 1/2 cubed, which will be 1/8. Of what it originally was. Isn't that? God damn it. Yeah, I wanted to do the next exercise, but apparently it's an example. Anyway, I really wanted you to try this exercise because it's interesting and it's quite complicated to get right. And they asked them a lot in the exam, but apparently I forgot to actually add an animation here. Anyway, so we'll go over the solution together, and then you can try to. So an isotope X has a half-life of 2 minutes. It decays into an isotope Y, which is stable, just meaning it doesn't decay more. Initially, there's nothing of isotope Y. How much time needs to pass before the ratio between the atoms of Y and the atom of X is equal to 7? So I tend to solve these problems by drawing a table. Each of you will have a different method. This just works for me because it's very organized and it's really easy to see. So you start with one sample of x, just set a number. You can also set a letter if you want to be fancy, but a number. It's 3 half-lives, so 6 minutes. Yes. Because after 1 half-life, the sample of x is 1/2, and the sample of y is also 1/2, since you'd have one half of the initial isotope decay. So the ratio of y to x is again 1/2 over 1/2. Then after 2 half-lives, you have 1/4 of the sample of x, since you'd have 1/2 of 1/2 decay, which is 1/4. And the sample of y will be the rest of that, so 3/4, since you always have to have the same amount of particles. And after 3 half-lives, as we stated earlier, so you have 1/2 cubed, so 1/8. Sample of y will have 7/8, and therefore the ratio will be 7:1 of ratio of y to x. I really advise drawing a table of these because it just makes it really easy to follow, and it will also make the examiner really easy to see what you're doing. And it just looks very neat, but that's just a pet peeve. Are there any questions about this exercise? Okay, yes. So isotope Y is stable, meaning it does not decay. Can you, if I draw, can you see it? Can you see me drawing? Okay, cool. Awesome. So I'll explain that in a second. So you know that the isotope of X has a half-life of 2 minutes, right? So this half-life is usually represented by this, and it just tells you that it's 2 minutes, meaning that if you have a sample of X after and it decays into Y, so anything that was X and that decays becomes the element Y. So you start with, let's say, you start with a sample of x of 1 because it's just easiest to operate it with 1. You can call it A, you can call it 2, it doesn't matter. But you start, let's just say you start with 1, since it's the most simple thing to start with. We're just making an assumption that we start with one sample of x. And at time 0, since it states that there is nothing of isotope y, we know that the sample of y will be 0. So after 1 half-life, since by the definition of half-life is the time it takes for half of the atoms or half the particles to decay, and they decay to y, you'll end up with 1/2 of x and 1/2 of y, since 1/2 will have decayed into y. So that's after 1 half-life. Then after 2 half-lives, so you have 1/2 of 1/2, so you'll have 1/2. So you'll have 1/2 times 1/2, which is equal to 1/4. This will be what's left of x, because well, after wait a second. Since half of this decays into that, so 1/4. And then you had 1/2 initially, and you've added 1/2 of 1/2, or actually you've added, well, of 1/2 plus 1/4, which is 3/4, since 1/4 has also decayed. Or another easy way to do it, it's they always have to add up to 1, because particles just don't disappear from thin air, so they always have to add up to 1. So 1/2 plus 1/2 is 1. 1/4 plus 3/4 is 1. They always have to add up to the original sample that you had of x. So that's an easy way to do it. If you want to really understand what's going on, then you'd have 1/2 of y, and then the other fourth that has decayed from x, which has become y, which is equal to 3/4. And then the same applies to here, so you have 1/8 that decays, and then you have 3/4 plus 1/8, which is 7/8. Because half of the sample again has decayed. Do you understand it better now? Other people gave good explanations that are easier. Okay, cool. Awesome. So let's continue. So other definitions which are important and can be asked are mass defect and binding energy, or mass defect. I don't know how to pronounce it, but the mass of a nucleus is smaller than the sum of the masses of its individual nucleons. This difference is known as mass defect, and it's represented with the letter delta. So it's a very important concept, and it has to do with the formula of E is equal to mc squared, which I typed here. So what happens is when you have all these nucleons together, they share part of their mass becomes energy, binding energy, to keep them together. If you find, say you have a mass, say you have, like, I don't know, say you have a nucleus of mass m, and let's say that the overall energy, that the overall mass of when you weight the nucleus is, so let's say you have the nucleus has mass m, but you know it has, say, n protons and neutrons. So you do n times the number of protons plus n times the number of neutrons, assuming it has the same number of protons as neutrons, and you realize that this is greater than m, so greater than the mass you weight of the nucleus, meaning that there's some leftover energy that has just disappeared, or it's like there's some leftover mass that has been converted into binding energy. And this binding energy is the minimal energy required to separate the nucleons. So if you want to break the nucleus apart into its individual components, you need to at least apply the binding energy. And the greater the binding energy, the more stable a nucleus is. So so the highest binding energy, which I think is in the next slide, is iron, which is why you can't have anything more stable than iron. It's the most stable element. And here's just an usual conversion. Usual conversion. You don't need to know it, but 1 atomic mass unit has energy 931.5 milli-electron volts. Is that clear? This is, I think I explained myself horribly, but I hope you understood what I was trying to say. So binding energy is the energy needed. Yes, it's the minimum energy to split the nucleus, and it's the energy keeping the. Yes, I would recommend you go for the first definition, but technically it is the difference between the masses of bound and unbound states passed to energy, so converted to energy with Einstein's formula. So anyway, this is. Well, this diagram is just the diagram of binding energies. It's really useful for nuclear fission when nuclear fusion and nuclear fission when we get that in a second. But as I was stating earlier, this is the mean binding energy per nucleon, and this is the number of nucleons in the nucleus. As you can see, the highest point is here, which is iron, which is actually part of the reason some of you who I know there's no astrophysics exam this year, but like those of you who have done astrophysics or know a little about it. Stars leave the main sequence after they start forming iron. Actually, stars can only form up to iron. They don't leave the main sequence when they're forming iron. But stars can only form up to iron due to nuclear fusion because it has the highest binding energy. And as we'll see in a second, fusion depends on binding energy and a change in binding energy between two elements. So this is the most stable element. So, fusion and fission. Fission is the separation of a nucleus into two smaller nuclei, which are photons and into smaller nuclei, energy, photons, and neutrons. So, for instance, this is one that happens, I think, in nuclear, and I think this one is the one that happens in nuclear plants, but I'm not sure. Where you have a uranium atom, and you feed it a neutron. So that it becomes unstable and splits apart into a zircon atom and a tellurium, I don't know how to say that in English, and three electrons, which actually these just mean that it's a chain reaction. So that these three neutrons can use another uranium atom to start the reaction again. The fusion is the union of two lighter nuclei to form a heavier nucleus and some energy. So, for instance, this is the fusion of just a hydrogen atom with a helium atom to produce another atom of helium and a neutron. The energy released is the difference in binding energy from this two atoms and this one. So this one will have energy, binding energy A, this one will have energy binding B and C, for instance. So you'll have A minus B minus C, and that difference in energy is what is released by the nuclear process. I think there's a couple exercises in my presentation later. So for fusion to occur, temperatures need to be very high, and that's very important because you need to overcome the electronic repulsion in the nucleus, which basically means that since, as we stated earlier, there is huge repulsion because everything is positively charged in the nucleus, and the nuclear force is very short in range. You need to have really high kinetic energies to be able to overcome that. It's actually called a Coulomb barrier, but it basically just means that they exert a force outwards which repulses protons. And so you need to have really high kinetic energies to overcome that Coulomb barrier, which you can literally think of as a barrier. So you can literally think of as, let's say, like something like that. And this is just energy. And if you have anything less than, say, this energy right here, which is the minimum energy needed to overcome the Coulomb barrier, you won't be able to fuse two elements together, which is why fusion is so difficult to sustain, and it needs this like 14 million degrees Kelvin and stuff like that to be able to happen, and why it only happens in the core of nucleus or in the core of stars, because the temperatures there are absurdly hot. And then you have artificial transmutation, which is just the process through which a nuclear species transforms into another nuclear species. So so it's basically you can basically create gold from lead, but the price of creating that is more expensive than the gold itself. So you're better off buying it, but you can if you want to. And Rutherford was awarded the Nobel Prize in 1908 for this discovery, which you don't need to know. But are there any questions regarding anything that I explained? The Coulomb barrier is not something that you will be asked, but it's really interesting to know and really useful to know, and it helps you understand why nuclear fusion is so complicated. Okay, well then I'll move on. Particle physics. So nowadays the standard model is the one that dictates how particles interact. It assumes that particles, which are known as elemental particles, are indivisible. So they cannot be made of other particles. There are three types, which are quarks, leptons, and exchange particles. Exchange particles are associated with the four fundamental forces of nature, and there is also the Higgs boson, which is actually, I'm not entirely sure, it just gives particles its mass, but I'm not entirely sure where it comes from, so I'm not going to try to explain it, and you definitely won't be asked it. So quarks are elemental particles that combine to form hadrons. So hadrons are a combination of quarks, which there's two types of. You have baryons, which are composed of three quarks. Protons and neutrons are baryons. And you have mesons, which are a hadron composed of a quark and an antiquark. So you'll have something like an up and an anti-down, for instance, is a meson, or a strange and a anti-charm, something like that. I'm just making these up, so they probably are violating some law, but they basically consist of two particles, which are a particle and an antiparticle. But you don't see many mesons around. Like the ones you see most often are baryons. Color is a fundamental property of quarks. There are three colors, and it doesn't mean that when you look at a quark, it will be the red, green, or blue. It's just the way we define a property. Quarks actually don't have any color. They're just too small to actually absorb any light. But it's just a property, and there's a whole bunch of up, down, and strange are particles, so they are elemental particles. I actually don't know if there's a, actually, there isn't. So up, down, strange are elemental particles, so they are quarks. So quarks, there's 6 types. You have up, you have down, you have strange, you have charm, you have top, and you have bottom. And you have this in the formula booklet, so I think it's added here. But these are just the 6 quarks, and they can combine to form different elements. For instance, a proton has an up and a down charge, and a down quark. A neutron has a down, and an up. And they each have different charge. So, for instance, down has 1/3, up has 2/3. No, you're not. I don't think you're supposed to remember the combination of quarks for a proton and a neutron. No, you can deduce it though by knowing the charge, because you know that. So essentially, these two quarks, they are stable. They won't decay. Oh, I don't know. I did 82 years ago. These two elements, these up and down quarks, are stable, meaning they won't decay. So most of the particles you see in a day-to-day basis are well, which are basically protons and neutrons, are made of up and down quarks. Strange, charm, and top and bottom are not so stable, and they're very rare, so they decay into other particles, which we'll see in a second. But with Feynman diagrams, but just think protons and neutrons are made of up and down quarks, and then you can deduce their composition by knowing that a proton has charge +1. And so, since you know the charge of a down and an up quark, you just need, and there's 3 quarks total, you need to know that it has to, actually that's -1/3, not +1/3. So you need to somehow add up to 3/3, which means you can only have 2/3 plus 2/3 minus 1/3, which means this is an up quark, this is an up quark, and this is a down quark. That's one way to remember if you want to work it out. And same goes for neutrons, so just same logic. The charge of an anti-down would be literally the opposite of the charge of a. Actually, well, that's another way to do it. The charge of an anti-down would be the opposite of a down quark. So if a down quark has charge 1/3, I can't write. That's a 3. An anti-down will have charge of -1. Actually, no, other way around. This has charge of -1/3, so an anti-down will have charge of 1/3. By the way, this bar at the top signifies that it's an antiparticle. So if you see this, that's an anti-up. If you see this, that's an anti-down, anti-strange, anti-charm. You get the idea. So here are some of the conservation laws. Well, actually, these things that are conserved. So quantum number is a number or property which is used to characterize the third particle. It's a bit more complex than that, but you don't need to know the actual ins and outs, and I didn't study them for this, so I'm not going to go over them. But numbers include charge, the baryonic number, strangeness, Reynolds number, and color. Then you have baryonic number, which is it's an intrinsic property of quarks. Yes, the session is being recorded. All quarks have a baryonic number assigned, which is 1/3 for quarks and -1/3 for antiquarks. Antiquarks meaning any antiparticle that is a quark. So anti-down, anti-strange, anti-charm, anti-top, anti-bottom, and anti-top. And anti-up, my bad. So then there's a strangeness, which is a quantum number, which is applied only to hadrons. And all hadrons with a strange quark have a strangeness of s+1. And also something that I forgot to add is all hadrons with an anti-strange have a strangeness -1. Leptonic number is a quantum number which is applied only to leptons, and each lepton has a leptonic number of L plus 1. It actually divides into 3 generations. So you have leptonic muonic number, leptonic electronic number, and leptonic towonic number, which actually I don't know if it's explained later. It maybe isn't, but that's maybe more quantum. I think I explained it a bit later. If not, I'll add it to the end of the presentation. Antiparticle is a particle corresponding, so as I explained earlier, each particle has a corresponding antiparticle, which has the same mass, but opposing charge and quantum numbers. And some particles, like the photon or the graviton, are their own antiparticles. And this happens when they are electrically neutral. So any electrically neutral particle, actually it doesn't happen all the time. There's an anti-neutron, for example. But photons and gravitons, for instance, don't have an antiparticle. They are their own antiparticle. Then this, the Rutherford-Geiger-Marsden experiment. Let me just check what else. Oh yeah, okay, never mind. The Standard Model is explained a bit later. So we'll go into more detail in a second. The Rutherford-Geiger-Marsden experiment is a really famous experiment, which helped to show the size of the nucleus. It was the first estimation of the size of the nucleus. So all particles are directed to a thin gold foil, and thin, I mean it's monatomic in length. It's very, very thin. Most particles either go through with Bernoulli deviation, so they basically just go like that, or they bounce sort of like this, so they have a huge deviation from, so they come like this and then bounce like that, and bounce with an angle, with a very high angle. This dispersion implies there is a force causing the deviation, which is a Coulomb force. Well, the purpose of neutrinos and neutrinos, I'll get to that in a second. I'll get to that when I explain the Standard Model and conservation laws, but so I'll explain that in a second. So the dispersion, this angle theta right here, implies that there's a force causing the deviation, which is the Coulomb force between positive charges in the alpha particle. So you bombard alpha particles here. So these are just actually that's a 4. So you bombard alpha particles, and then you see that some of them bounce back, like that, and you kind of see you check your particle detector, and you see that there's some that are like here, and then you see dots like over here as well. And so that means that there must be some positive charges in the alpha particles and some positive charges in the monatomic gold foil that are repelling each other and causing it to bounce back with such an exaggerated angle. And because the force is so large, because it's such a huge deviation, there must be a very small separation, and the denominator must be very small. And so which means that the positive charge of the atom must be coalesced into a very small space. Basically, so you have to know that the size of the nucleus compared to the size of an atom is tiny. It's ridiculously tiny. I don't remember a comparison here, so I'm not going to make up anything, but it's very, very small. And so this was how they first showed that there is such a thing as the nucleus, and that this nucleus contains all the positive charge of the electron. Neutrons were actually discovered later. And then from this, Rutherford deduced that the nucleus of an atom is a sphere with radius r to the 10 r. Well, it has 10 to the minus 15 meters, which is femtometers. But you don't need to know how he actually showed this. It has to do with the angle of deviation in another formula. Anyway, so after Rutherford's experiments, new particles were discovered. So he discovered the proton, he discovered a nucleus. Then the proton was discovered in 1930, which is what gave, it's what gives nucleus or atoms its electrical charge, its positive electrical charge. I know it said Rutherford discovered it, but it wasn't Rutherford. Hold on. It wasn't. But the neutron and positron were discovered later in 1932. And between 1950 and 1960, lots of particles were discovered thanks to the particles accelerators in the world. In 1964, the existence of 3 quarks was postulated. The combination of these 3 quarks explained the properties of our particle discovered by then, and then 3 other quarks have been discovered since. So you don't need to know this. This is just a bit of history that I added. But so these 3 quarks are the up and down, and then I assume it's the strange atom, and then the charm top and bottom were discovered later, since they're a bit more rare. The Standard Model. This is very important, so I'm going to devote some time to this. It explains all the properties of all known particles, and it's based on 6 quarks, which we went over earlier: up, down, strange, charm, top and bottom. 6 leptons, which are the electron, the tauon, and the muon, and their corresponding neutrinos, which are there for conservation of momentum. I'll get to that in a second. But you have the muon neutrino, the muon neutrino, the tauon neutrino, and the electron neutrino, which are represented by the Greek letter neo, which kind of looks like that. And the exchange particles, which are the photon, the bosons, which there's 3 types of, and the gluon, which I actually don't remember how it's represented in with the letter. I think it's just represented with like this when you draw a Feynman diagram, but I'm not entirely sure how it's represented with a letter right now. Anyway, quarks. So this is in your formula booklet. So you have so you have three quarks. So they're basically in pairs. You have like this pair right here, which is up and down. Then you have charm and strange and top and bottom. But you have in each pair you have one that has charge 2/3 and the other one is charge minus 1/3. So the quark, because it doesn't, the anti-strange has strangeness of 1. Did I say? I said earlier it has strangeness of minus 1. Did I? Yeah. So anti-strange has strangeness of 1 and strange has strangeness of minus 1. So I made a mistake here. So this is supposed to be a minus 1, and this is supposed to be plus 1. It's just how it's defined. I think I don't think it's just how it's defined, and they chose a minus 1 for some reason. Anyway, so yeah, these up, charm, and top will have charge of 2/3, and down, strange, and baryon, and bottom, my bad, have a charge of minus 1/3. They all, as we stated earlier, have a baryonic number of 1/3, since that's just by definition any baryon, since it's made of 3 quarks, has to have a baryonic number of 1, or an integer baryonic number, which usually means it has a baryonic number of 1. And that just makes it so that every quark has to have a baryonic number of 1/3. And then all the antiparticles will have the charge with a minus sign, the baryonic number with a minus sign, and the strange with a minus sign. So for the proton, this is supposed to be H. Since the proton has charge E, it can only be formed by 2 ups and 1 down, as we stated earlier. So you can only have 2/3, bloody hell, 2/3 plus 2/3 minus 1/3 to give you 1, since it has charge E. And the neutron, having neutral charge, can only be formed by 2 down and 1 up. Well, it can technically be formed by other combinations of atoms, but you know that it's up and down because they're the stable ones. The other ones are not as stable, and so you won't see them as often. So, how do I move that? Well, okay. So, per strange quark in a hadron, the hadron has a quantum number of strangeness equal to minus 1. As such, the baryon, for instance, the baryon sigma, which is an up and a strange quark, has strangeness minus 1. And I'll look into this later. I'm pretty sure this is pp plus, but I'll check that later and keep you updated. And I'll re-record this and upload it to YouTube. But an anti-down, so for instance, the baryon sigma plus has an anti-down and anti-down and anti-strange has strangeness plus 1. In every interaction, baryonic and leptonic numbers must be conserved. In strong and electromagnetic interactions, strangeness is conserved, but it is not conserved in weak interactions. We'll see some examples later. So basically, if you see an interaction where strangeness isn't conserved, that means that it's a weak interaction. You can say it immediately. Confinement, which is isolated quarks, and consequently their color cannot be observed. If enough energy is applied to a hadron, the separated between quarks can increase momentarily, and a quark-antiquark pair can be created in that void. At that point, the hadron gets rid of the quark-antiquark pair. So basically, what confinement means is you can't see the color. You can't know what color an atom is made of, or a quark is made of, because as soon as you try to split it, it's kind of like trying to split a magnet. If you grab a magnet and you cut it by half, you won't end up with just a positive pole. You'd end up with a smaller positive and negative pole, but you'll still end up with two poles. It's the same kind of principle. If you apply enough energy to separate the if you apply enough energy to separate a quark-antiquark pair, what you'll see is that you need to put in enough energy to create another quark-antiquark pair, which basically will create a quark-antiquark pair, and you'll get back to the beginning. Conservation laws, which is really important. In particle interactions, energy, momentum, charge, periodic number, atomic number, and color are conserved, among other things. The most notable exception is strangeness, which is only conserved in electromagnetic interactions and strong interactions, but not in weak interactions. This is very important. Particle interactions. There are four fundamental interactions in nature that differ in the force that causes them, which we said earlier. So we have the electromagnetic interaction, which acts in particles with charge, the strong interaction, which acts between particles with color, so quarks, weak interaction, which acts on quarks and leptons, and gravitational interaction, which acts on all particles that have mass. In particle physics, gravitational interaction is negligible because of the small mass of the particles. Feynman proposed a new way of interpreting particle interactions. For electromagnetic interactions, he considered that two particles exchange a particle when they interact, which is an exchange particle. In the case of an electromagnetic interaction, for example, it's a photon. And other interactions, such as the weak interaction, exchange a boson, or a strong interaction exchanges a gluon. Gravitational interaction exchanges a graviton. But the graviton has never been observed. But that's another deal. And then by emitting a photon, for instance, in the electromagnetic interaction, the momentum of the emitter electron changes, and so does the momentum of the receiver. And this change in momentum, because if you remember from topic 2, the force is defined as the change in momentum over time. So this change in momentum, this delta P, is what we observe as the force, as the exchange force. So Feynman diagrams, he realized that an interaction in electromagnetism can be represented pictorially with a single vertex of interaction. So for instance, in this diagram, you can see that there's two vertices of interaction. There's one here and there's one here. So there's this one where the electron emits a photon. So there's this electron coming, it emits a photon, and then it changes direction. The other electron absorbs the photon, it also changes direction. So there's these two vertices of interaction. Here, actually, this is just particle. Never mind. That's just supposed to say particle. I think it was in Spanish, which is why I translated it. But in this figure, the vertices of interaction are used again twice to represent a pair-antipair annihilation. So here, what a pair-antipair annihilation is, actually, if you check, I think it's explained in detail in one of my quantum notes, which I posted in the channel I pinned, if you want to go into detail of what it actually entails. But basically what happens is, if you have a pair, so say you have a particle of mass m, and an antiparticle which also has mass m, since they have opposite charges, they will collide, and they will end up creating a photon, which with energy is equal to 2mc. So it's going to have energy. So they're going to collide, and they're going to create a photon with energy 2mc squared, which is going to be the energy. This is assuming, of course, they had no momentum, or that the momentum got completely cancelled out, which doesn't happen. If they had a lot of speed, the photon may start with a greater energy. So it's going to start at least with 2mc squared of energy. And then what happens is this photon can then again split up into two particles. So it's going to have energy greater than, actually, it's always going to be greater than 2mc squared, because the particles need to have some momentum. Then these particles, so it will split up again and spontaneously into a particle and another particle, which may be, again, in this case, for example, it may be a positron and an electron. This is a positron. Or it may be something completely different. They can split up, but they have enough kinetic energy into a proton and antiproton, or into even bigger elements, or into even more like heavier particles. But that's usually what you see. The most common one is a positron and an electron, because they are the ones with the lowest energy. Also, something to note is that antiparticles are represented with an arrow in the opposite direction. So usually you have that, so that it's just that. So they basically what it means is if you have time flowing in that direction, right, which is then you have electron, or like you have positrons kind of quote unquote flowing backwards in time, which is not actually what they're doing. It's just a convention to represent them. But it's they're usually represented going backwards in time rather than forwards in time. This is another interaction that I've seen in a couple of exams. The values of interaction have been used 4 times, and this is just represents the dispersion of a photon with another photon. So yeah, so there's a vertex of interaction here, a vertex of interaction here, a vertex of interaction there, and this is just 2 photons combining into 2 other photons. So there is 2 photons, then they exchange a particle, then this photon exchanges a particle, and you just end up with this kind of loop. Weak interactions have several vertices of interaction, as we'll see in a second, and they're a bit harder to depict, but they're not that hard. I think this is the last slide. For instance, in this one, you have a quark and another quark, which they interact, and they form a W- boson. It depends on in order to know what boson is being formed, you need to look at the charge. So because charge will always be conserved, right? So so since charge will always be conserved, you can check what type of boson you will have depending on what charge is missing. So let's say you're missing. Let's say this has charge of. Let's say this has charge of 2, and this has charge of 1, right? So there is some charge. There's a actually I don't think that's going to work. But this W- boson is going to have a charge of -1. So that wait a second, that just doesn't add up. So we have 0 here and then -1 here. There you go. Let's say this is a neutral quark, and this is a quark which has charge -1. I can't come up with any examples at the moment, but when they interact, you see that charge from here to here isn't conserved. But when you look at the boson, you see, oh, it's so since this charge has charge 0 and there's a difference of -1 in charge, then the boson has to be a W- boson, since that has negative charge. Similarly, this is also what happens here in when you have a neutron or a muon, or sorry, a lepton decay into its neutrino. Since these have charge of -1 and these are neutral in charge, then this has to be a W- boson. because it has to have charge of -1 for charge to be conserved in interaction. And then you can also have, for instance, a quark or lepton interact with itself, and since there won't be a difference of charge, so this is going to have charge Q, and there's also going to have charge Q, there's not going to be any difference of charge, but there is an interaction, and so the boson has to be a C, well, a C neutral, which is, or just a C proton, which is neutral. And then lastly, there is the W plus boson, which is like the W minus boson, but it has a positive charge. So if you have a quark which has charge +1, or actually no, a charge that has charge 0, and you end up with a quark that has charge 1, and this interaction will actually, this should be 0, my bad, because the time flows in Feynman diagrams, time flows in that direction. So this is going to have charge 0, and this is going to have charge -1. Because time is defined as flowing in from left to right instead of from right to left. I apologize for that, but I hope that's clear. And so in this one, you'll have charge of 0 here, you end up with charge of 1. For instance, or and therefore, you know, since time flows in this direction, always from right to left, unless it's explicitly stated otherwise, assume it's from right to left. Then you have that this has to be a W plus boson, since well, yeah, since the difference in charge is a +1, you need charge to be conserved, so you need a W plus boson here. Actually, do you? Hold on. Charge. Yeah, I think so. Basically, just look at conservation of charge, see what's missing. Actually, no, rather, this, I mean, hold on. No. So if this is a -1, then this has to be a +1. So this has to be, so in order, my bad, I made a mistake. Sorry. Forget what I said about these two interactions. The other ones are correct, this one isn't. So in this one, since time is flowing from right to left, you have a 0 quark, and here you have a charge -1. So this one is going to have a +1. So that +1 and -1 is 0. So you end up with the same charge all around. So charge is conserved. Because the difference in charge is +1, so therefore you need to have a -1 somewhere, so that the charge is conserved around the interaction. And then for the other example, which I'm going to do here, you have, say, let's say this is a W plus, right? So this is going to have a charge of +1. And if you have a charge of 0 here, you know that this has to be a -1. So that -1 plus 1 is equal to 0, and the charge here is conserved as well. Is that clear, or am I explaining myself very poorly? I know I made a mistake at the beginning, so about this one. But am I explaining myself correctly? Okay, so you guys understand what's going on with the bosons, right? Okay, cool. Gluons, I actually haven't seen any questions about gluons, but they're a bit trickier. Well, they're actually not that tricky. But if you ever see this notation in a Feynman diagram, that just means it's a strong interaction. I don't have any examples in this presentation, but if you need to, I'll upload some presentation. I'll add them to the presentation and upload them to YouTube later. But yeah, are there any questions about this topic? Anything you'd like to know? How do we know where to place each particle? Like, what do you mean? You just, like in the Feynman diagram, where do you place them? So you'll have your initial particle on the right side usually, and your end particle on the left side. So and then, so this is your initial particle. This is your final particle. And then in the middle, you just draw whatever happens with that particle. So if it's an EM interaction, you'll draw kind of like a squiggly line. Um, if it's a weak interaction, you'll have to show them interacting. Actually, usually what happens is you draw a line representing what kind of particle it is. There's something like that. And then on the left hand side, you start by showing your initial particle. On the right hand side, you show your final particle. And then you draw the line in the middle representing what kind of interaction happens between them. In the case of weak interactions, there has to be some. You need to show both arrows intersecting in a vertex of interaction, because what is happening essentially, right? This is but you could interpret this as a quark emitting a boson and decaying into another quark. So it's not technically two particles interacting; it's just one particle decaying into another one. So, for instance, you have, like, say, this quark just goes this way, and then you have time flowing that direction. So you have it going this way, and then it changes direction, meaning this is a vertex of interaction. So something has to happen here for it to change direction, for it to have a different energy and change momentum. And then in that vertex of interaction is where you draw the particle. And then obviously this W minus boson can itself decay into other things. Like, for instance, this one, right? This is a W minus boson. You can have a W minus boson decay into a lepton and a neutrino, or you can just have it stay like that. It doesn't really, or you can have it like, see, for instance, here. This could be a W minus boson. So you could have some kind of interaction going on here, say something that looks like that, right? Some sorts of interaction that emits a W minus boson that then itself can decay into an electron and an electron neutrino. But you usually always have time flowing in that direction. So you start on the left hand side and you go towards the right hand side. Is that understandable, or do you want me to try explain it another way? Well, the antiparticle has to be flowing backwards in time, right? So if you have time flowing in this direction and this were to be an antiparticle, then you'd need to have that flowing in that direction if this were an antiparticle. But here, since it is just another quark interacting, right? Since since this is just another quark, it tells us it's another quark. We know this isn't an antiparticle, so we just know they're kind of colliding into each other and emitting a W minus boson. But if it were the same part, but yeah, so you can draw antiparticles. Just draw them opposite to time. So if you go back here, just draw antiparticles. That's not. Where is it? Here. Just draw antiparticles. Always opposing the flow of time. So in this case, for instance, you know that the flow of time has to be downwards because this is an antiparticle and it has to be flowing opposite to time, so it has to be flowing kind of backwards in time, whereas the particles flow forwards in time. Does it matter? But is that clear? I don't know what exactly you're asking, but no. They absolutely don't go backwards in time. No. It's just a visual representation. It's so we just show how they go backwards and frontwards in time, but antiparticles don't actually flow backwards in time. No. They absolutely travel forwards, but since we need some way to tell them apart, we just draw an arrow flowing backwards. But no, as far as I know, there's nothing that actually travels backwards in time. So are there any more questions? I hope I answered yours correctly, Nor. I'm not sure. If I did, if not, we can we can just talk later in the physics channel. Okay. So are there any more questions before I stop the recording? And I'll upload this to YouTube later because right now I have shitty Wi-Fi. It's gonna take like 18 hours. Is it possible? Yeah. I mean, you could do that, but it's just a visual representation, really. I explained it. I explained it in one of the sets of notes that I sent, that I pinned in the channel. Actually, I don't know if I pinned it. Let me see if I did. Which one of the pinned ones? Because yeah. So in lecture 7, you can actually see where why pair production occurs experimentally. If you want to have a look at that, it does explain a bit more of the physics behind it and the physics behind spectroscopy. It's a bit more advanced, and you definitely don't need to know it for the exam. But if any of you is curious about why we represent them like that and the Dirac theory of atoms, which is a bit antiquated. I think there's a more modern one involving fields and stuff, which I'm not aware of, but that one can at least help you get an idea of why it works like that. You can check lecture 7 in the pinned comments, in the pinned notes, in the pinned whatever, in the pinned messages in the channel, and there it shows there is a bit of a talk about where antiparticles come from and where pair production and annihilation comes from experimentally, which I think is very interesting. So feel free to read that and ask me any questions if you do have them. But if that is all, I will stop the recording now, and I hope I'll tell you later when I explain topic 12 and when I have an idea of topic 3 as well. Is the purpose of neutrinos, antineutrinos, and particles just to keep electron neutrality? Neutrinos are there to keep momentum rather. Neutrinos, antineutrinos, and antiparticles. No, antiparticles are just. It's actually, I think it's explained there why antiparticles exist. But antineutrinos and neutrinos are there because of a because what they were discovered because of conservation of momentum, because we were seeing that the conservation of momentum wasn't happening in some interactions, and so since conservation of momentum is a fundamental of physics, it had to be conserved. We just looked until we hypothesized there must have been a particle that is electrically neutral, that has very small mass, but can carry away some of the momentum for this momentum to be conserved, and then we later discovered neutrinos and antineutrinos. But antiparticles in general, no, they're not there to keep electron neutrality. I don't really know why the reason particles like antiparticles exist. I don't think they are just. They definitely do exist in real life. Like they're not something we made up to conserve electrical charge. There is something that exists, and I don't really know why they exist. I guess they're just there. But did I get kicked out? I got kicked out. Whatever.